Welcome to Dataless U. I'm Paul, coming to you from Brooklyn. Today we are going to take a look at U-Substitution. So open up to page 392 of good old James Stewarts' single variable calculus. We're going to do three problems, number 17, 27, and 33. Let's go. I've already got the questions up here on the big board, and you'll notice that each of these requires a different sort of trick. Let's start with number 17. It's asking what is the integral of sine of pi t dt. So for this one we're going to do a classic U-substitution. We don't really know the integral of the sine of pi t, of any t with a coefficient, in this case pi. So it's a simple little U-substitution. We say, okay, let's let u be that pi t. Okay. Well, that means our du is pi dt. Okay. Now, notice we already have our dt, so that's nice. But what we need is we need to put in a pi, right? So we'll sneak a little pi right here. Right now we have pi dt, a little sleight of hand. But you can't just put pi into an equation. So what we'll do is we'll take out a 1 over pi. 1 over pi times pi is just 1, so we haven't fundamentally altered the equation. That is the nifty trick of U-substitution. Now we can go ahead and evaluate this integral. So it's as if we are saying the integral of the sine of u du. Right? And of course our 1 over pi is going to hang out for us out in front. Well, we know the integral of the sine of u. The integral of the sine of u is negative cosine u. So we can take our negative out and we still have our 1 over pi out here. And then we have cosine of u. And I'm going to speed things up, and instead of writing u, I'm going to just plug our u, which was pi t, back in. So, and then, of course, plus c. Don't forget your plus c. And that's it. So, the integral of sine of pi t dt after U-substitution equals negative 1 over pi cosine of pi t plus c. Not bad at all. Let's take a look at a more complicated U-substitution. So let's say we have, what is the integral of secant cubed x times tangent of x dx? And you're looking at that, you're saying, oh boy, that looks like a handful. If you are in fact working out of James Stewarts' textbook, I would heartily encourage you to memorize the integrals on page 369. So on page 369, we see that the best substitution for us is going to make the u secant of x, and that's to the first power. So why to the first power? Well, because we know from derivatives that the derivative of secant x is in fact secant x times tan x dx. All right, so what do we have here? Look, we already have tan x dx, and I'll do a kind of a squiggly underline here because within that secant cubed x, we do have 1 secant x, right? So essentially what we're doing here, and I'm going to take our time with this one and write it all out. We're saying the integral, and we're breaking it up, and I'm going to take a full moment here to break it up, of secant x, right, so just one of them, times, I'll use parentheses, oh sorry, there's 2 left over, don't let me confuse you, there's 2 left over. We took just one of them out, times tan x dx, and those are just sort of there waiting for us. We need those. All right, and look what we have. To go back to magenta, which is sort of our U-substitution color, there's our u, just the secant x, so it's essentially u squared, and there's our dx. That makes sense? So this is dx, or du, sorry. This is du, we can turn that into a u, oh, not so bad. And this is our u, but it's actually u squared. Make sense? So let's just go ahead and evaluate. Once you've done the U-substitution, usually the evaluation isn't so bad. So we're taking the integral of just u squared du. That's it. Right? Which equals, of course, u to the third over 3. And so our last step is just to plug our u back in. Well, what was our u? Let's take the 1/3 out and make it look pretty. We'll put it right here. 1/3, remember our u was secant x. So you just go back and look at the magenta, and we see that our u was secant x, which is now cubed. And don't forget your plus c. So that's a more interesting one. And it takes a little practice mastering the skill of really determining what your u is going to be. So let's look at this third and final one for this video. We have here a tricky situation. We have the integral of 1 plus x over 1 plus x squared dx. Now you might spend a lot of time thinking, well, could I make my u x squared? Could I make my u 1 plus x squared? But none of those are going to quite work because the du for those would be 2x, and we can't really get a 2x out of 1 plus x. So with a little practice and with some familiarity, what you'll notice is that the trick for a question like this is to actually break it up. We can break that fraction up. We can say that that is the integral of 1 over 1 plus x squared, right? That's the first half, plus we can break it up and say plus the derivative of x over 1 plus x squared. And that is the hard part, really seeing that. Oh, and don't forget your dx's, right? Now, why is this going to work for us? Well, the integral of 1 over 1 plus x squared is simply the inverse tan of x. And again, I would refer you to page 369 for the list of integrals which you really want to memorize. So that's easy enough, right? We could just say this is equivalent. This integral here is equivalent to the tan, and that is the inverse tan of x, right? Now this one's a little trickier, right? So we're actually going to take our time with this. We're going to go back to magenta, and here's where the U-substitution comes in. Here's where we can now say, we can make our u the denominator. We can say the u is 1 plus x squared, right? And so du, well, the integral of 1 is 0, so then we're just, the derivative of 1 is 0, and the derivative of x squared is 2x dx. And now we're back to this game of trying to see if we have that. Well, look, we have dx, obviously. We have x, so all we need to do is slide that little 2 in here. And then, of course, you can't just put a 2 in without taking out a 1/2. Right? 2 times 1/2 is 1, so we haven't fundamentally changed our equation. And now we have a much simpler integral to take. We have the integral of 1 over u du, right? And we're only moments away from the end. The final answer then is the tan, the inverse tan of x, that was the first derivative, plus, don't forget the 1/2, 1/2 times the integral of 1 over u, which is a simple natural log of u. And to save time, I'll just go ahead and plug our u right back in. That's 1 plus x squared plus c. Don't forget your plus c. So again, these are 3 different kinds of U-substitutions. Number 17 is a straightforward U-substitution. We have to put in a pi, take out a 1 over pi. Number 27 is a little bit more complicated. You have to really think about what your u is going to be. If you make u secant x, we have a perfect du and a simple integral of u squared. And number 33, the most complicated, there wasn't really a perfect U-substitution off the bat. We had to split it up and then see that we had a nice clean integral giving us the inverse tan of x, plus a relatively simple u substitution then giving us 1/2 the natural log of the u, which is 1 plus x squared. I hope this makes sense, and I will see you in the future.